Now, to set up effective algorithms for solution of nonlinear problems, we will have to understand the process of linearization of a nonlinear function. In this course, we will mostly be interested in vector or tensor functions. Let's say a tensor function A, which is a function of the displacements u. It can obviously be functions of other vectors, but in this course, most of the functions that we encounter are functions of displacements or generalized displacements u. Now, the definition of linearization of A is done in the same way as we had done for the case of the first variation. So, the first variation of A was denoted by delta A, which is a function of u and delta u, and it was defined as the directional derivative with respect to u of A in the direction of delta u, where delta u was a virtual displacement, was a first variation in u, which we could picture as an error that we have made in u or a small perturbation in u. Now, the definition is exactly the same in case of when we linearize. So when we linearize, so linearized version of A is like the Taylor series of a function where we have stopped at this first term. So Taylor series, remember, f x plus u is fx plus f prime x evaluated at x times h and so on. If we stop at the first term, this is what we get. Okay, so similarly, the linearized form of A is A evaluated at u plus the directional derivative of A in the direction of the increment in the displacement vector, which we call triangle u. So it's the same expression but evaluated at triangle u, evaluated for in the direction of triangle u rather than in the direction of delta u. We will see the distinction now, distinction in a little while, but right now just understand that this quantity and this quantity are in spirit different kinds of quantities. So, but the operation is exactly the same. So linearization of f at u in the direction of triangle u would be f at u plus directional derivative of f with respect to u in the direction of delta u, which means that we already know del u f first variation of u. So this we already know is del 0 of um, del u. This is del 0 of del u. So to calculate this quantity, we just replace this by triangle u, and then we have del 0 of triangle u, and that's what we have put here. Similarly, linearized version of C, f transpose f, is C evaluated to u plus this directional derivative. Again, we have del C, which we had defined as 2f transpose del epsilon f. We had done this problem. So just replace this by triangle. Remember, delta epsilon was half was this. So everywhere replace this by, and you get delta epsilon. So that delta epsilon would go in here when you have to calculate delta c, and that is this quantity. So this is the same thing as c evaluated in the direction of delta u. So this replaces this can be replaced here. So very often when we don't have any chance of getting confused, regarding um, what this what the directional derivative is taken against, we will denote this quantity as dA in the direction of delta u. Often we will even drop the delta u when it is clear that we are taking an increment in u. We will just simplify the equations a bit. So this will denote directional derivative with respect to u of a in the direction of delta u. So we will both use this, or sometimes we will even be more brief and use just this. Uh, when we use this, it will mean that we are taking it with respect to u in the direction of delta u. Now we have already seen that delta A is the directional derivative with respect to u of A in the direction of the first variation of u. This is how we have defined it, and this delta A is itself a function of u and delta u, and can be a nonlinear function of u as well, which means that we can linearize delta A as well. So we can actually write d delta A, which would be delta A evaluated at u plus the directional derivative with respect to u of delta A in the direction of triangle u. So this is the quantity that we will have to define, and if you look at it carefully, you will see that this has to be evaluated using the classical definition of the directional derivative as d epsilon of delta A u plus epsilon triangle u. This is according to our definition. This is how it will have to be defined, and you will see that this definition is exactly similar to the definition of the second variation that we had stated earlier, except that in the second variation this was delta u, and here it is triangle u. Here it is triangle u. Apart from that, uh, when you are taking the linearization of variation of a function, you are actually taking the second variation of that function with delta u replaced by triangle u. Now you have two quantities. One is the first variation of u, one is triangle u and increment in u, and it is usual to confuse between the two. To understand the subtle distinction between these two quantities, let us do a problem. So let us calculate the linearization of the green Lagrange strain tensor. Let us calculate the directional derivative of the green Lagrange strain tensor in the direction of delta u, triangle u, that is an increment in u. Now, let us first look at delta E. So we know delta E, we know delta C actually. We know delta C is F transpose delta epsilon F, 2 times that. E is half C minus I, so delta E would be a function of U and delta U, half of this, so that will be equal to F transpose delta epsilon F. We have already seen that delta epsilon is half um, plus, that is, it's the first variation of the small strain tensor. It's the first variation of the small strain tensor. Now, this is what I have written here. And let us take a look at the first term. So the first term here is F transpose spatial gradient of delta U transpose F. If we write it in indicial notation, it we will write it as, let's say we are writing ijth component of this, then we will write this as F ki that is F transpose, and then uh, for the spatial derivative again transpose. So we'll write it as, let's say, mk and f mj. This is how we will write it. Now uh, now this quantity we have discussed this before. The k will come with the nabla, so this would be nabla k delta um f mj. So the first index goes with delta u, the second one goes with the nabla. So this is del xk del capital Xi, that is the definition of fki. This is del small xk, then delta um and fmj. So this is again a chain rule. So del xk and del xk here. So this will boil down to del capital Xi. So what you have now is del capital Xi of delta fmj. And if you now convert this to the vector notation, this is the spatial material derivative of delta u, and because this m comes here, this is transpose of it times f. So this is mi. So what you have is mi fmj. So you have delta 0 u transpose f. So that's what you have here. Okay, let's look at the second term. Let's erase this. Let's look at the second term. The second term is f transpose this is the second term. Again, if you convert it into indicial notation ijth, so this will be fki, then nabla delta u k m f m j. This is how the ijth component will be written, and here fki is del xk del capital Xi. This is del delta u k del small x m and f mj. So this is what we have, and um, and then you will be left with small xm times small xm by capital Xj. Again, this is the chain rule. You have the repeated index here. So this will lead to fki times del uk by del capital Xj. So this is del 0 delta u, the kjth component, times fki. So this is if you convert it into bold notation, this would be f transpose of del 0 delta u, which is what we have here. So we have again converted these nablas, the spatial nablas, to the material nablas here. And now once we have delta E, the first variation of E, we need to take the um, second variation of E in the direction of delta U, which will be this simply is directional derivative with respect to U of delta E in the direction of triangle U. So this is what we have to evaluate. Now we will evaluate it on this expression. We'll evaluate it on this expression. But before doing that, let us understand that delta triangle of u, the increment in u, and the first variation in u actually do not affect each other. So one is not a function of the other. Uh, to see that, this is how we this is the best way I could think of showing it to you. This is the initial configuration omega 0, final configuration omega, and this point capital P is mapped onto small p, and we are taking a, uh perturbation field. So at every point, so this is the actual u, and at every point we have made some error which is delta u. Okay, so we have made this error, and uh, this is delta u, and now this configuration is my erroneous configuration. This is the erroneous configuration that I have got. I should have got this yellow one, but I have got this dotted one because I have, at every point I have made this error, and now I'm going to give an increment in displacement to the erroneous configuration, because this yellow configuration I don't actually have. I think that this erroneous configuration is my deformed configuration. So the when I give the increment in u, I give it on the erroneous configuration. Therefore, when I give this triangle u, the delta u moves with it. So delta u and triangle u are perpendicular to each other in some sense, and one doesn't affect the other. So what we need to realize that delta u is unaffected by triangle of u, and therefore they are not functions of each other, and therefore when we take the derivative we should be careful not to try and take directional derivatives of the independent variations of the independent variable. So uh, d of d of delta u is actually 0. This is d of delta u in the direction of triangle u is actually equal to 0. So keeping this in mind, we will go back to our uh, expression for delta e, which has this, and we will now try to find this quantity. So let me write it down. This is delta e is half so this is delta E, we have derived this. And now when we do d of delta E in the direction of triangle U, we have to realize that this quantity doesn't get affected by this operation, and it is as if it's a constant here, and the only thing that is affected is this. Similarly here, this gets affected, but this doesn't get affected. So how does this get affected? So when I do d of this side, so I have to do d of this and d of this. D of f in the direction of delta u, we have already seen, is the directional derivative with respect to u of f in the direction of delta u, but we all in the direction of triangle u, but we already know f in the direction of delta u, so we know that this is equal to this. So this will become half of, this remains intact, this df becomes equal to this, and this df transpose becomes transpose of this, so this will be transpose, and this remains unaffected. So this is what it becomes. Now you can see that the first term and the second term are transpose of each other. So if you take transpose of this first whole term, this will come ahead and have a transpose, and this transpose will go away, will come behind it. So that's what has happened in this term. And you know that the a tensor plus its transpose halved is the symmetric part of the tensor. So this is simply the symmetric part of, we are using the fact that symmetric part of A is half A plus A transpose. We know that. Okay, so this is symmetric part of this tensor. So this is your directional derivative of delta E in the direction of triangle U, implementing U. This is what we have, and those steps are given here. Okay.